Hi guys, welcome back to Data Every Day. Today we're looking at a data set of budgets in a marketing campaign. So I believe this is synthetic data, dummy data, but we have data that says how much is being spent on different types of promotion for an advertising campaign, and seeing the number of sales generated from a given budget allocation. We also have a type of influencers that are being targeted. So we're going to try to predict the sales based on these four features. We're going to use gradient boosting to make the predictions, and usually with synthetic data, you can usually assume you'll get a pretty good fit if it was, unless it was generated with extreme randomness. So let's import NumPy and pandas for working with the data. And for visualization, we'll use pyplot and seaborn. And then for pre-processing, we'll use the train test split function from sklearn, along with the one-hot encoder standard scaler. Actually, we don't need the standard scaler. Because we're using a gradient boosting model, which uses tree boosting, with boosted trees, tree-based models do not need to be, you don't need to scale the data being passed in. So we won't use a scaler, just a one-hot encoder, column transformer, and pipeline. So that we can do the pre-processing within the pipeline. We don't have to, so we can pass in human readable inputs to the model. Let's go ahead and import all of that, and then load in the data using pandas.read CSV. So we can grab the file path to the CSV file up here. I'll copy it, paste it in, and we can take a look. And so this will be a regression task where we predict sales based on these four features. Let's get a little more information with data.info. We check for missing values. And it looks like we might have some missing values here, yeah. So let's get into pre-processing. I'll create a function called preprocess inputs that takes in the data frame and just makes a copy of it. And we'll add to this function as we do the pre-processing so we can see the result on a fresh copy of the data. So I'll pass data into the function, I'll store the result in X. Right now it's just a duplicate. I don't know how much, I don't think we actually have to pre-process these columns outside of the pipeline. The only thing we want to do is split and actually just split the data. Oh, actually no, we should fill missing values. So let's look at the missing values. X.isNA will give us a true in any spot we have a missing value. So if we sum this over all the rows, we'll get the number of missing values in each column. So we have 10 in TV, 4 in radio, 6 in social media, and 6 in sales. These are very small numbers considering how many rows we have. So we can just fill these with the mean of each column. It doesn't look like we have any missing values in the influencer column, in which case we would need to use the mode because we're using categorical data. But I also noticed that we have missing values in the target column. And so when you have missing values in the target column, the column you're trying to predict, you should drop any rows that have those missing values, because it doesn't make sense to fill the values and then try to predict on them, because you're predicting on fabricated data. Well, let's drop rows with missing target data. So how do we do this? We can actually, instead of taking the isNA matrix for the whole data frame, you can just do it for that sales column. What that'll do is give us a true in any location where down the column that we have a missing value. And you can actually use a true-false matrix, true-false array like this, a Boolean array, as an indexer for the data. As long as the length is the same as the number of rows, you can just plug this right in. If we want to index something in X, we can just take this and put it in as the indexer to get back just the rows where we have missing values in the sales column. You can see the indices here that we want to drop. We can get those with .index. And that will return just the indices we want to drop. So let's put this into our function up here. And let's just change X to df. That's the name of our data frame. And let's call this missing target rows. So these are the rows we want to drop. So df equals df.drop missing target rows from axis 0. That's the row axis. And since we're dropping rows, let's reset the index afterwards. I'll include drop equals true so the old indices don't become a new column. If we run this now, we should see this 6 should become a 0. So there we go. We did lose 6 rows, but that's okay. So we do have to deal with the remaining missing values. And these are all in numerical data, continuous variables. So we can just fill them with the mean. So let's fill remaining missing values with column means. So I'm going to iterate through the columns we need to worry about, which are these three. We'll say for column in this list, just clean it up a little. So for each one of these columns, we're going to take the column and use the fill NA function on it, which allows us to fill missing values with whatever we pass in here. So we're going to pass in the mean of the column, df sub column.mean, and then we're going to set that equal to the original column, like so. Alright, so now we should see there should be no more missing values. Everything should be filled in, so we're good to go. Alright, now let's split the data. So split df into x and y to start. So this is the y is what we're trying to predict. That's the sales column, so just the sales column. And then x is all the rest of the data, so we'll drop sales from axis 1, which is the column axis. So this should actually now return x and y, and we'll get them back over here. X should no longer have the sales column, and y is just the sales column. So now that we've done this sort of vertical split, let's do a horizontal split, where we'll set some for the train set and some for the test set. So that's our train test split, and we'll use the train test split function from sklearn to do this for us. We pass in x and y, specify a train size. So why don't we set 70% of the data to the train set, use the remaining 30% for evaluation. And then shuffle equals true. That's on by default, but it'll just shuffle the data before we do the split. And we'll give it a random state as well, which ensures the shuffle is always done the same way, and therefore the split is as well. Now that will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And these sets I want to return from the function. So let's grab them, return them over here, and then get them back over here. Now let's look at xtrain. So xtrain, just the only difference is that it's been shuffled and we have 70% of the data here. Ytrain you'll see that the indices match up. Okay, so let's do training. So we have a categorical variable here. So we don't have to scale, but we have to one-hot encode this. I didn't do the one-hot encoding before. The reason is, let's say you want to deploy this model. A user would want to enter in a single value and to the model, right, for the influencer type. So a user doesn't want to enter in the one-hot encoded version of the influencer column. That doesn't really make sense to a human, although it's important to do for the model. So the pipeline allows us to enter in information like this, then do the pre-processing, and then get the prediction. So we're going to create a sub-pipeline inside our main pipeline. So let's do this. I'll create the main pipeline first. This will be a pipeline from sklearn. The steps here is a list of tuples defining each step. The tuple should contain the name of the step and then the actual step object. So we want to pre-process, so I'll call preprocessor, and this is the thing that will do the one-hot encoding. And then we'll have the regressor. This will be our gradient boosting regressor. So we want to design this preprocessor to one-hot encode the influencer column. So let's create a one-hot encoder from sklearn. And I'll just enable a sparse equals false so that it doesn't return a sparse output. And I'm going to embed this one-hot encoder in its own pipeline, where the only step is one-hot encoder. So I'll give it the name one-hot, and that will be our one-hot encoder. Oh, there we go. All right, and let's call this nominal transformer, since this is used on nominal features, and it transforms them accordingly. So this is nice, but the model right now doesn't know which columns to use the one-hot encoding on. So we're going to use a column transformer for that. It's also from sklearn. Allows us to specify some transformers to use and which columns to use them on. This also takes tuples, where we specify the name, so nominal, the actual transformer, which will be the nominal transformer we just created, and then the columns we want to use it on. So just one column here, which is influencer. Alright, and you want to make sure to include remainder equals pass-through, which basically says any columns that are not affected by the transformer here will stay in the dataset. If you don't include this, they'll be dropped. So then we'll call this preprocessor. Now you can see how it all fits together. The preprocessor is what happens first when we feed the data into the model. The preprocessor looks at the influencer column, uses this one-hot encoder on it, encodes it, and then passes the result, all the columns, not just the one it targeted, into the regressor. The regressor then makes the prediction and returns the result. Alright, so there's our model. And let's fit the model on X train and Y train. Whoops, not test, train. Alright, and it's fit. So it has applied the one-hot encoding and then the gradient boosting regressor. Alright, let's look at the results. So for the results, I'd like to return two metrics and plot the predicted values against the actual values. So let's get a set of predictions called ypred. That'll be model.predict on the test set. So ypred looks like this. It's just a set of predictions, and we want to compare this to ytest. If we look at a NumPy array of ytest, you'll see they're the same format. They should be close to each other. We want these to be as close to ytest as possible. So we can measure the error between them with ytest minus ypred, and this will be our error. So a useful metric would be to know the average error across all examples. Now, the way it is right now, if we took the average, let's see what happens, numpy.mean of this, you see it's very close to 0. But that doesn't necessarily mean our model is good, because you notice that we have positives and negatives that would cancel each other out when we summed across. So we can counteract this by squaring the results, and this puts it all on the positive scale. Then if we take the mean, we get this is the mean squared error. So this is more realistic. Only problem is it's in the squared unit. So if you look at the data set, we're in millions of maybe dollars. Where's this from? I'm not sure exactly what currency it's in. Let's just say it's in dollars. Then the sales are in millions of dollars. And you can see our average error is not in millions of dollars, but in millions of squared dollars, or squared millions of dollars. So because it's in squared dollars, squared millions, we'll square root it to bring it back down into the original unit. And so this is now called the root mean squared error, and it's this is on average how far we are off in a prediction, but in the original unit we're dealing with. So this is saying, let's call this RMSE for root mean squared error. We're about $6.3 million off on average across all predictions. And if you look at the data, the sales data, it's actually pretty good, because we're in the hundreds of millions. See what is we can look at the distribution of the sales. If we look at ytest.describe, we can see the distribution. You can see most of the data. It's spread from 31 to 358, with a median of 193. So there's quite a large range here, and we're only off by about 6.3 million. So actually, it's a pretty good RMSE, considering the data set. So another way we can evaluate it is asking how much better is this model than having no model at all, or having a baseline model. So what I mean by baseline model, so let's say we just had ytest and we had no information about each example to make predictions. The best thing we could do in this case is to predict the mean of the column. So this would be our prediction for every single example. And if we take y-test and now find the error between these two things, this is a valid error distribution, just the way we had up here, right? Between our predictions and the test. This is between the mean and the test. So another way we can evaluate the model's performance is saying how much better is our model than just predicting the mean. So one way to do this is to use the R-squared score, which is a nice metric that basically works by just squaring this result, like we did before, and then summing across. And so this is the sum of squares for the baseline model. And then we do the same thing for our model. So we take y-test, subtract our predictions, square this thing, and then take the sum. And then we compare these two things. So we could just put them over each other like a fraction, like this, and that would be a proportion from our thing to the from our error for our sum of squared errors to the baseline model's sum of squared errors. But this isn't so interpretable. I mean, obviously, the closer to 0 this is, the better, because that means our error is close to 0. But what's even nicer than this is taking that whole thing and doing 1 minus it. Sorry, 1 minus. And this is known as the R-squared score. So all 1 minus does is it has the effect of sending the whole score to 1 when we have a 0, when we have 0 error. And it becomes a measure of reduction in error distribution between the baseline model and our model. So when our error is 0, this whole thing goes to 0, and this whole thing goes to 1. And on the other hand, if our error is much, much bigger than the baseline model's error, this whole thing goes to positive infinity, and 1 minus positive infinity is negative infinity. So the R-squared score, which is this thing, we have a very good one of 0.995, has the highest possible value of 1 when you have 0 error, and the lowest possible value of negative infinity when you have much, much more error than the baseline model. So let's call this R2, and let's put these side by side, and let's just print them out nicely under this. So we'll print out the RMSE. Let's display it to 2 decimal places, format it with RMSE, and then print out the R-squared score. We'll display this to 4 decimal places, format with R2. Alright, so there it is. So we're about $6.33 million off each prediction on average, and we have a 99% reduction in the error distribution, in the variance of the error distribution for our model over the baseline model. Alright, so the last thing we can do to sort of evaluate the performance of this regression model is to plot our predicted values against the actual values. So we'll create a new pie plot figure with a figure size of 10 by 10. It should be a square since we want both axes to have the same scale. And then we're going to use Seaborn's scatter function to generate a scatter plot. On the x, we want to plot the predicted values, so ypred, and on the y, we want to plot the actual values, so ytest. We'll give it some axis labels. So on the x is the predicted values, and on the y is the actual values. We'll give it a title. This is actual versus predicted values, and show. We got a problem. Oh, that's, I think it's scatter plot. Alright, and here it is. So this is really good. Now we are working with synthetic data, so we have to realize that you know, in real life, if you're working with a real world data set, it would probably never be this nice. But you want this plot to be along the y equals x line, along the predicted equals actual line, because this means that our predicted values are very close to the actual values. Now you can see it looks like we have about 4 bad predictions, only 4 across the whole test set, and I'm not sure exactly why those ones are. Maybe they're outliers. I'm not going to go into that right now, but you can see that we do have a really nice fit here. because our predicted values are really close to the actual values. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.